Hi everyone, and welcome to the channel. So are you curious what's inside a 2 kilowatt electronic load? Well, stick around because I'm going to show you all the parts and pieces that are inside one of these electronic loads or Dynaloads. So I recently picked up this unit, and it's made by Transistor Devices Inc. or TDI. It's their model RBL 488 100 300 2000. Now there are many different models in the RBL 488 series. They all have different voltage, current, and power dissipation ratings. In fact, I have another RBL 488 model. It's rated up to 800 watts, but this model has double the voltage and double the current capability of that other model. So I was definitely interested in this unit when I saw it. Now, this unit and the other unit that I own both have the exact same user interface, same control panel, so it makes going between them very easy. In fact, most of the RBL 488 models that I've seen use the same type of control panel, but there is a second style that I've also seen, but it seems like the style that this uses is the more common version. This model, again, is the 100 300 2000. So what those numbers mean is that the maximum input voltage is 100 volts DC, the maximum current this can draw is 300 amps, the maximum power dissipation is 2000 watts or 2 kilowatts. But you can't do the maximum voltage and current at the same time because of course that would far exceed 2000 watts. And this has protection circuitry inside of it that prevents over current and over power and other situations that would damage the instrument. At 300 amps, the maximum voltage is just a little bit under 7 volts. But at 100 volts, the maximum current is 20 amps. Now, the reason this is completely stripped down the way you see it is because when I purchased this, it was sold as untested and unknown condition. It wasn't even shown powered up or anything like that. So I took a chance on it. So when I received it, I took the top cover off, had a look around inside. It was extremely dusty and dirty. Went ahead and powered it up, and it seems to work okay. So there really won't be troubleshooting because I don't see any issues going on. But like all the test equipment that I get in, I always like to take it apart and clean things up and really inspect it and check things out and make sure everything's in good condition, just a good thorough visual inspection. And sometimes that means quite a bit of work, but oftentimes it's worth it because you'll come across some issues and things that might be hidden. In this case, the dust and lint and other things inside of the instrument really couldn't be cleaned out any other way. It completely needed to be stripped down. So the way that you see it sitting here, I've done quite a bit of cleanup on it already, and I'll put a picture up on the screen the way that it looked in this bottom part of the chassis when I got all the parts and pieces removed, and again, compare how that looked to the way it is now. You can see that I've cleaned up quite a bit. And these fans were very dusty and dirty, so those have been cleaned up already as well. So I don't want to bore you with the cleanup and just removing lint and dust and just using compressed air. I just took this thing outside and blew a lot of it out. I didn't want to do that in the shop here. So clouds of dust were coming out of it. So that's all been taken care of, and all the individual pieces, as I've been removing them, circuit boards and things like that, have all been cleaned up. So I'm basically right at the point now to start reassembly. So I'm going to show you the various parts and pieces on here, and then I'll start putting things back together, and I'll show you those components and boards and modules and everything as I start reassembly, and we'll build this thing back up. Now, I've lost count, but at the last check, I had removed over 90 screws from this thing. There's a lot of hardware, and in fact, there are parts and pieces all over the workbench, little containers of hardware, so I don't get things crossed up and in the wrong order and so forth. And I set up another table for some of the modules and the circuit boards to be organized on because there's just far too much to put all out on the workbench here. All right, so let me position the camera a little bit different. Let's start taking a look around on this part of the chassis. By the way, the reason that this is still assembled here is because this piece and this piece are riveted to this bottom panel, so you can't take it apart any further. I don't need to remove this circuit board to clean it. It can just stay there, and I've already cleaned these fans because there's easy access the way it's sitting here. So this is the front of the electronic load. The control panel fits in this area. You can see how the wiring has connectors on the ends. So everything plugs together, very modular construction. So for this complete disassembly, I didn't have to desolder anything. And the fan motors are in good condition, so they spin very easily. You can see how they rock back and forth, and that's always a good sign. So the magnetism in the motor is able to rock just a little bit when they stop. It means that the bearings turn very freely. So if you spin a fan motor like this, and they just come to a stop and they don't want to rock back and forth, kind of a stiff feel, it means the bearings are on their way out. So these were extremely dusty and dirty. That's all been cleaned up. Now these are 24 volt brushless motors, and there's some control circuitry, and these run on less than 24 volts for the low speed, and that voltage is increased if more cooling is needed. So there's a big vent in this front corner, and also a vent across the top of the instrument, and air is drawn in this way, goes through the fans, and exhausts out the back. So at the back of the electronic load, along this lower edge, the AC line input and a voltage selector switch. There's a terminal board right here for some external connections that can be made. One of the connections is for the voltage sensing, so there's some jumpers. If you remove those jumpers, then you can remote voltage sense, but with these jumpers in place, then the voltage sensing is done inside the electronic load. It's off of these wires, so these connect to the positive and negative distribution buses, which I'll make that connection later on. And then everything on this board goes off on this ribbon cable. There's a GPIB interface with another ribbon cable. Capacitor right here, one side's connected to earth ground or the chassis, the other side on this ring terminal connects to the positive distribution bus. So that capacitor is for some noise filtering. And you can see right here there's a red and black wire, this connector. That's for powering the relays that turn the electronic load on and off. There's a whole bunch of relays that mount up in this area. We'll get to those later on as well. You can see the AC wiring coming in right here is not all that large, but that's to be expected because this doesn't require that much power to actually operate. You know, there's some power, about 15 watts or so, to operate the fans and then obviously the electronics. But again, not that much is required. There's a tag on this back corner and it says 100 volts at 2.1 amps, 120 volts at 1.8 amps, 200 volts at 1.8 amps, and 220 volts, 0.9 amps, 47 hertz to 63 hertz. So, you know, a fairly low amount of power actually to operate this electronic load. So this is the microprocessor board. This ribbon cable goes to the GPIB connector. This wiring goes to the front panel displays and keypad. Nothing plugs into these two connectors. This ribbon cable and this connector is coming from that rear panel terminal board, but there's another very large circuit board that fits along this outer edge, and that's what this plugs into. And you can see the microprocessor board plugs into this other circuit board right across here. So let me just move this down a little bit here. So there's a very large ribbon cable, and again there's an outer circuit board that fits in here, and I'll be installing that next. So this is linking this outside circuit board with everything else. And then this wiring right here is coming from the power supply, and it plugs into this outer circuit board. So obviously some power is being distributed back through this ribbon cable to the rest of the circuitry, along with a lot of other control signals. If I just lift this up, see some other circuitry under there. And right here, this wiring goes to the relays. We already saw the other end of this wiring at the back panel. This is for the fan speed control, this little connector right here, and this again plugs into this outside circuit board that fits along the edge. And this notch right here will have a ribbon cable that passes through here. It plugs into the outer circuit board, and we'll take a look at that ribbon cable a little bit later on when I start reinstalling everything. All right, so the next circuit board is in place, and that digital board I just showed you is behind right here. So this circuit board looks to mostly be analog circuitry. There are a whole bunch of OP27 op-amps scattered all over the board, not to mention quite a few calibration pots as well. So I'll put some close-up images of this board on the screen, and if you're interested, just pause the video, take a closer look. Now this electronic load had the factory original calibration seals on all the covers, and I had to break those seals, so I'm the first person in here since it left the factory, so there's really no reason to think that any of these calibration pots would ever have been messed with. So I have all the wiring attached, and there's one more ribbon cable that goes right here. Next I need to start installing the power handling modules. So there are 9 of these modules, they're all identical, and this is where the power dissipation happens inside the electronic load. So I'll put a couple close-up pictures of the circuit board. If you're interested in taking a closer look, just pause the video. I'll also put up an example of some of the lint and dust that was along one of the modules, the edge between the circuit board and the heatsink. And basically all the modules look like that, and really a lot worse because that picture was taken after I had blown a lot of the lint and dust out with compressed air. But there was a fair amount that was quite stubborn and had to be knocked away with a bristle brush. So if I take the module here and just turn it, you can see there's this large aluminum heatsink, and the circuit board is attached to it. And then between the circuit board and this heatsink are the power handling devices, basically power FETs or MOSFETs. So there are 8 of them on each module. And then these modules are just mounted in here, one next to the other. You see all the holes in the bottom of the chassis, and then the 3 screws in the bottom of the heatsink. And then, of course, the top cover has the screws that go through the cover and into the top of the heat sinks as well. So it makes basically a channel. The air is going from the fans through the heatsink fins and then exhausting out the back. And if you look right here, you can see there's these distribution buses, the positive and negative goes back here. And there's distribution buses along the back edge, and we'll get to those a little bit later. So all of these modules are operated in parallel, and they're always connected in parallel at all times, and all 9 modules are operating together all the time. So if the electronic load is dissipating 1 watt or 2,000 watts, it doesn't matter. All of the modules are sharing the load, no matter how large or small it is. The 9 modules at 2,000 watts, just take 2,000 divided by 9, you're asking each module as a maximum to dissipate 222.22 watts. So you can imagine these get quite warm, but of course with the air blowing over them, it's dissipating that off as the heat. But again, this does get quite hot in operation. There's a big warning note on the top cover mentioning that it gets quite hot. And then each module, again, has these 8 power FETs on it. So if you have 8 power FETs and 9 modules, there's 72 power FETs total. So 72 FETs that are actually dissipating the energy, as basically turning it into heat. And you could think of those power FETs as variable resistors. So they're turning on more or less. The resistance of those FETs is changing, and that of course changes the amount of current that flows and the amount of power that's dissipated in the electronic load. So 2,000 watts divided by the 72 FETs, you're asking at a maximum for each power FET to dissipate about 27.78 watts. Now I'm not sure exactly what part number was used for these power FETs, and I don't want to take the module apart any further because inside on the module, you kind of see maybe along this edge right here, but there's like a sheet. It's basically the same size as the circuit board, and it's an insulating thermal sheet between the power FETs and the heatsink, and I don't want to disturb that and take that apart. If that insulating sheet were to tear or be damaged somehow, it would be a big problem. So again, I don't want to take this apart any further, so I don't know the part number of the FETs that were used, but with 27.78 watts, that's obviously well within the spec of whatever they used. But you have to remember these are getting very hot in operation, and they get derated for the amount of power they can dissipate. Now, this electronic load can also handle up to 300 amps. So take 300 amps and divide it by 72. At a maximum, you're asking each power FET to pass up to 4.17 amps. I noticed when I removed the modules along this back edge and also in the middle, they had some thermal compound. That's all been cleaned up, but I'll replace that as well. They didn't have any thermal compound on this other end. Maybe they didn't want to really have a lot of the heat going in this direction of the chassis. You have the fans and some other electronics that way, but maybe they felt that it should be absorbed over into this side of the chassis. So I'll just return the thermal compound the way they had it originally. They did not have any thermal compound on the top side of the heatsink where it touches the top cover. All right, the first module is in place, and you can see I marked this module as 9. The reason for that is because when I was removing the modules, I started on this side and just worked across that way. Now all the modules are electrically identical. They all work in parallel, so they could be installed in any position. The electronic load is going to work perfectly fine. You can see this ribbon cable that ties all the modules together. So the ribbon cable starts at the analog control board and just distributes the signals across to all the modules. So the reason that I numbered the modules is just for mechanical reason, so that I could return the modules to the same location that they were removed. So for example, suppose that these distribution bars that come across to more distribution bus bars at this back edge, maybe something is torqued just a certain way and it fit just right. It would be probably easier to have it in the same location rather than moving it to a different location and have something out of alignment just a little bit. So again, I only did it for mechanical reasons. Electrically, they could be in any position. Now these modules all look exactly the same and they're built to very tight tolerances, so they very likely could be in any position. But again, I figured it did fit properly when I removed everything, so why not just put it back in the same order. Now I already mentioned that each of these modules has 8 power FETs or MOSFETs on it. A FET is a field effect transistor. So power FETs or MOSFETs have the distinct advantage over a bipolar transistor of being very easy to parallel. So you'll always see in modern electronic loads the active device that's dissipating the power is going to be a power FET or a MOSFET. And in this case, we're paralleling 72 of these devices in here. And again, it's very, very easy to do so because they cooperate very well and they won't go into thermal runaway. So a bipolar transistor has the disadvantage that if you take two bipolar transistors, and even if they're spec'd to be identical, if you put them with no other support components around them to prevent the issue, the two transistors by themselves, one will start to warm up a little more than the other. It warms up a little bit, it conducts a little heavier, now it gets a little hotter, it conducts a little more, it gets a little bit hotter. It quickly spirals into a runaway condition, and it goes into what's known as thermal runaway. So to prevent that with bipolar transistors, you use emitter resistors, or what's known as a ballast resistor. It's a very common technique, and it works very, very well. But you can still have some problems, and in electronic loads where things are running very hot and you have many, many devices that are paralleled, power FETs and MOSFETs really have an advantage over using bipolar transistors. Years back, it was common to see bipolar transistors in electronic loads because of the technology of the time. So I have two of the DLP series electronic loads by transistor devices, and those electronic loads do use bipolar transistors, and of course every one of them has an emitter resistor on it. And in the DLP 5060 1000A, did a video on that one, and it had a failed transistor in it, probably because it went into thermal runaway at some point. So again, the power FET or MOSFETs have a very distinct advantage of not having that problem. And again, they're very, very easy to parallel. All right, all the power modules are in place. So now it's time to install the negative input bus bar. And you can see this large stud is part of the bus bar. The head of this bolt is soldered on, as well as being tightened down with this nut right there. So this bus bar fits in down here, and it's attached by all of these screws to the bus bars that go into the modules. So when I took these screws out, I just returned them back into these places so I didn't lose them. So I'll remove all those screws, get this bus bar down in here, put the screws back in place. This terminal, or the wire right here that comes off of that capacitor, needs to be attached, and the black wire right here also needs to be attached. All right, so the negative bus bar is in place. Now I need to install the positive distribution bus bar, and that's this assembly right here. So this complete assembly attaches to the modules on each of the bus bars off the modules all the way across. And if you look here, you can see the positive input stud attaches to this large bus bar. This bus bar attaches to one side of each of the relay contacts. The other side of the relay contacts goes to these threaded inserts in the circuit board. So those threaded inserts are how the screws attach down through these bus bars off the modules. And if you look along this edge right here, there's this kind of a gold or amber colored tape. And the purpose of that tape is just to insulate the bus bar because they don't want to short circuit if an object would fall into the electronic load. And there's some large vents along this back edge. So this is very close to those vents. They just wanted that for protection. Now the purpose of these relays is so that you can disconnect the electronic load from the source that you're testing. So the current that comes in divides 9 ways because there's 9 relays, and it divides evenly because each module is drawing the same amount of current. So for example, if the electronic load is drawing its maximum at 300 amps, then each relay would be passing 33.33 amps, just 300 divided by 9. Now each relay has contacts rated to 70 amps, so the maximum current capacity of this assembly would be 630 amps. So that's well over spec for the capacity of the electronic load. And these orange colored capacitors that are next to each relay, those are across the contacts of each relay. If I turn this a little bit here, you can see there's a connector on the board right there, and that connector is for this wiring right here, and that's what powers the relays. Now with 9 relays, when they turn off, there's going to be a sizable kickback voltage, because when the magnetism collapses around the coil, it induces a voltage, and that voltage is in the opposite polarity of the applied voltage. So you want to clamp that kickback voltage, and if you look right here, there's a diode on the board right there. So that diode is electrically across all the coils, because again, they're all in parallel. So that diode normally is not conducting when the relays are turned on, but when the source voltage is removed, then this diode conducts that kickback voltage, because again, the kickback voltage is the opposite polarity of the applied voltage, and that's when this diode conducts. So the diode, again, is in reverse polarity from the applied voltage. And right here you can see this red wire that has to attach right down in here, the terminal. So that's the voltage sensing, and it's on the unswitched side of this assembly. All right, the next thing I'm going to do is install the back panel. And this panel adds support for these two studs. So it's a good idea to get this panel installed next, because without this panel in place, these studs sticking out don't have a lot of support. And you can see how they flex around like that. The entire assembly moves. So as I'm working on this, if I tip it up or was doing something and it ended up bumping these studs, it could put a lot of force into the wrong location and cause some damage. So I'll get this taken care of next. All right, next I'll get the side panel in place. It fits right here, and I'll get the other side taken care of as well. All right, next I need to install the power supplies. So there are two power supplies that fit in this front area. They're both linear type power supplies as opposed to a switch mode design. So here's the first power supply, and this is for powering the fan motors. So you can see the AC line comes in here, power transformer, bridge rectifier, large filter capacitors. I tested both of those capacitors. They check perfectly fine. Handful of support components. The fan motors plug in on these connectors across there. This large heatsink has a voltage regulator on it. It's an LT1083. And it looks to me like what they're doing is controlling the fan motor voltage with this regulator, and this support circuitry is electronically adjusting this regulator, and the signal for this support circuitry is coming from that analog board that we saw earlier from that far side. So as the fans need to run faster, the voltage is increased off of this regulator. And then over here is the second power supply. Very heavy transformer on this board. So this powers everything else in the electronic load. So the AC line comes in, this connector here, and this connector right there, and these connectors over here are AC pass-through, and the fan power supply we just saw is powered off of one of these connectors. So the AC line comes in, powers this transformer, and then continues on and powers the other transformer. And then down in here, some bridge rectifiers hiding down in there, kind of dark. Get that touched up a little bit there. You can see them right down in there. Whole bunch of filter capacitors. Again, I tested all of these capacitors. They check perfectly fine. They weren't messing around with filtering. There's a lot of capacitors on there and some high values. Whole bunch of voltage regulators on heat sinks. The output voltage is on this connector right here. Not a lot of other support circuitry going on this board, so pretty straightforward design for a power supply, just producing a number of different voltages. So I'll get these power supplies installed, continue on. All right, so the power supplies are in place, and this connector plugs onto the front panel. So pardon the camera movement, let me just get you over to this other location on the workbench. Get this touched up a little bit. So let's take a closer look at the front panel. So I took everything apart because I want to clean these display windows. They have kind of a scum and a buildup on the inside of these windows, so I'll get that taken care of. I've already cleaned the front side, but I noticed after cleaning them it still had kind of a buildup on this side, so I'll work on that. On this circuit board right here, you can see one of the LEDs right there is bent kind of at an awkward angle. So it's leaning over that direction. So I'll desolder it and I'll straighten it out and put it back on the board. The reason that I don't want to just try and bend it over to straighten it is because that could very well crack the body of the LED. And the reason that I want this to be straight is because the tip of the LED is supposed to fit into a little hole in the front panel to illuminate the indicator. And the way this is right now, I don't think that that's fitting very well, and it's probably flexing this LED over, like that, just kind of bending it to make it fit. So I'll get that taken care of. And over here you can see the board just needs a little bit of general cleanup. A rotary encoder has kind of a dust and scum built up around it. So I'll get all that taken care of. And if we take a look on this circuit board here, this is for the keypad. And it might not be real obvious on the camera, but those gold-plated traces that make up where the buttons are at for the contacts have kind of a scum and build up on them as well. So I'll clean up all of those. And when those get dirty, you have that issue where you're pushing buttons really hard trying to make a connection. So now's the time to get all that cleaned up. They look kind of shiny on the camera, but to my eye, off camera, and when I look at them kind of at an angle, they have a dull film to them. They catch the light now and they look clean, but in reality they do need some clean up. Just a contact cleaner will take care of that. On the other side of the board, a couple components right here, but really not much else going on. And then this connector right here connects over to this part right here. That touched up there. So the boards just stack up. And on this rubber part for the keypad, be very careful with these. You never want to touch that conductive rubber button. It's down inside there. So careful when you're handling these. On this side, I'll go around and clean like that. I'm going to clean the buttons where they reach through the panel. There's a little bit of dust that's kind of down inside there, so I'll get that taken care of. So I'll do all of that and get this all reassembled, and we'll continue on. All right, so the cleanup on the front panel is complete. It's reassembled and back in place. So the only thing that I haven't put back are the top covers. You can see those sitting right there, and the other one right there. So of course you wouldn't want to run the electronic load under high power dissipation with the covers removed because you don't have proper cooling on the heat sinks. But for this initial testing, the load won't be dissipating that much power, so it's perfectly fine to leave the covers off, and I'll return them as a final step. Now, I'm very pleased how these display windows cleaned up, especially this LCD window. It had a lot of film and kind of a scum that had built up on the inside of this window, and I noticed that when I powered up the electronic load initially, this LCD was very hazy and it wasn't very clear. So I'm pleased that the window was the problem and it wasn't something wrong with that display. So I think it'll look greatly improved now, and I'm curious to see how it looks when I turn this on. There was a little bit of a film or kind of a scum on these other windows as well, but a lot more on this window. I don't know, maybe something spilled in from the top or what was going on there. All right, so of course this is an AC line operated device, so if you're following along, you're definitely doing so at your own risk. Take care and be safe, especially around AC line operated devices. In this unit, there's exposed AC line in this front area, and on this transformer in the corner, there are two pins right on the top that have white wires going to them. You may have seen that when I was showing that power supply a little bit earlier in the video. And there's AC line on those two pins, so you definitely wouldn't want to come in contact right in that corner. So again, if you're following along, you're definitely doing so at your own risk. This is being powered off of my isolation transformer for safety, and that's a must on AC line operated devices, and especially when they're being used like this with the exposed areas, things are opened up. All right, so I'll try and power this up. If everything comes up to, powers up, comes to life, then I'll turn on my DC power supply. I'm using the Sorensen SRL40-25. We'll give this some voltage, and I'll go through a couple of the functions and features. Again, I already tried this electronic load. I didn't notice any major faults or problems with it, so I'm not going to go through every possible feature and function on it, but we'll just get a feel for some of the basics. Now, this voltmeter, let me turn the backlight on here, so the Fluke 289, is connected across the terminals on the back of the electronic load. So this voltage should match this voltage, and of course that's what the power supply will be set at. I'll set it to 40 volts, that'll be a good test voltage. But as I draw more current, then this voltage will drop because there's some losses in the test cables and the test leads. So this voltage and this voltage will drop down, that's normal, but they should remain basically the same in value, together, but they'll fluctuate a little bit under load. And then this amperage reading right here should be the same as the amperage or current reading over here on the Keysight 34465A digital multimeter. So this is in series between the power supply and this electronic load. So again, we're watching for this to match right here. And of course, the product of voltage and amperage is the wattage. So just multiplying those numbers together should give us the reading that we see there. All right, so here we go. Let's see what happens. Okay, cool. Powered up all right. So right here it says RBL 100, 300, 2000. So that's the model, and then the firmware version 2.25. So excellent, no problems there. So let me go over here, and I'm going to turn on the power supply right there. Let that start up. Probably hear that other fan kicking in, so fans are running here, fans over in the power supply. Now before I turn on the voltage from the power supply, this range right here where it says low, medium, and high is of course the voltage range that you're using. So right now it's in the high range, and you can see like that, it says 100 volts and then 20 amps. If I go to medium range, then that's 50 volts maximum, and then the low range is 10 volts. So I'll put this in the medium range because we won't be going over 50 volts. So it changes the resolution that you have on the display. And then right here for the current, it's in low, so that's 20 amps maximum. Medium is 200 amps, and the high range, 300 amps. So low is perfectly fine. I won't be going anywhere near 20 amps because this digital multimeter and the current measurement is limited to 10 amps maximum. So we don't want to exceed that. All right, so let me go over here and give this some voltage. Okay, so this is just microamps. You ignore that number. It's very, very small, just a little bit of leakage current. So up to 20 volts. How's that looking? 20.9. Yep, it's an agreement there. $5.36. Adjusting it there. Okay, there's 40, very close to that. We don't have to be super precise. So that looks good. 40 volts, 40 volts, that's an agreement. Excellent. So let me go over here. So this is the constant current range, or constant current mode, which means that if the voltage fluctuates, the current that the electronic load wants to draw won't change. So I'll just go to 1 amp to start with. Current 1 amp, enter, and turn it on. Hey, how about that? Perfect. So 0.99, essentially 1 amp, and right there, 1 amp. Great. So that's working. And yes, that looks good. Now, this was 40 volts. It dropped just a little bit because, again, there's some loss in the test leads and the cables. So that's to be expected. So 39.96, 39.93, very, very close. I don't see any problems there. That's fine. So yeah, that looks good. The numbers match up. So if I go a little bit higher, let's go back here, current, oh, let's try 6 amps. So a little lot more of a drop there, but 6 amps, perfect. And the voltage is matching there, 6 amps, great. So everything's looking very good. I don't see any problems there. And again, with the constant current mode, if I lower the voltage down, you can see how the power dissipation, I'll just stop right there a little bit. You can see it went down to about 32 volts. Now the power has dropped down, but we're still 6 amps. Now, if you have a constant current mode setting here and you have constant current on your power supply, you want to make sure that the power supply doesn't try to go into the constant current mode because they'll fight each other and the voltage will collapse. So watch out for that if you're using one of these electronic loads. All right, so if I go over here, let me go back to, I'll just set this to 30 volts. So it's already close to that value. Let's go down about there, that's fine. So let me turn this off. So there's a constant power mode. So constant power will attempt to draw the same amount of power no matter what the voltage. So if I go to constant power and then go just, let's say 1 watt and enter, turn that on. Yes, so we have 1 watt and you can see very low current. But now watch what happens when I drop the voltage down, and I went to 1 watt just so I don't draw excessive current, because as the voltage drops, the current will start to increase. And as you start to get to low values of voltage, that current will go up very high. Now, in this case, it's not going to be excessive because it's a low power dissipation, but let's say you were telling it to dissipate 500 watts. As you start to go down to low voltages, that current would spike way up so that it continues to have the same amount of power dissipation. So again, it's holding at 1 watt all the way down to 5 volts now. Current has come up a little bit. So I increase this back up again. Okay, there's 40 volts again. And you can see how the current dropped way down. Now, constant voltage, you have to be careful with that. That acts like a Zener diode, or like a power Zener. So essentially, this will try to draw this enough current to hold the voltage at the value that you set. But if you don't have an external resistance, then this will draw extremely heavy current trying to maintain the voltage. So it has its place for testing, but you have to be very careful with that constant voltage mode. Turn this off here. Constant resistance essentially acts like a fixed resistor. So if I go right now, constant resistance high and low are just two different ranges, but they function the same way. So if I go constant resistance mode, and let's just go, let's say 20 ohms. So now this is acting like a fixed 20 ohm resistor that has basically a 2000 watt power dissipation rating. So there's 20 ohms, and 20 ohms, we're getting just about 2 amps, very close to that. About 2 amps right there. So perfect, no problems with that. Now, as with any resistor, if you drop the voltage, the current is going to fall as well. So if I take the voltage and start lowering this down, and of course that's exactly what happens. So there's about 10 volts there, very close to that. And you can see how the wattage, power dissipation dropped way down. Amperage fell way down as well, or the current. So again, just acting like a fixed resistance. And some of these other functions over here, the pulse modes or pulse generator for pulse load testing, it says short circuit right here. That's exactly what that means. It is a direct short. It essentially turns on all of those power FETs to their fullest. It completely saturates them, turns them on as hard as they can go, and it acts like a short. You have to be very, very careful with that mode, because obviously it's going to basically short out what you're testing. It's fine for testing power supplies that are intended to operate into a short, and you want to verify that. You never want to use the short circuit test on a battery or something, because it could cause extreme damage. The slave mode is for using this in different functions where you have other second units and so forth. And external programming is for external pulse modulation and controlling this with an external voltage, and that's done through that rear panel terminal board that we saw earlier in the video. Alright, so I'll turn this off. And I'll just reach over here. I'm going to turn off the power supply, just so that fan isn't running there. You can see those lights turned on momentarily. There's under voltage, over voltage, power limit, other faults that can occur, and it will tell you that and protect the electronic load as appropriate. So, if you try to turn the electronic load on and there is no voltage, or the voltage falls too low, you'll end up getting this saturation light that comes on. Basically means that all the devices, all those power FETs, are completely saturated. They can't be driven any harder. So, you know, quite a few different faults that can be displayed right here for different situations. All right, well, it looks like this electronic load is functioning perfectly fine. I don't see any issues with it. I'm going to use it extensively, give it a good thorough testing. I want to run it extremely hard under a heavy load, really warm it up, make sure that there are no issues whatsoever with it, and when I'm confident that everything is looking perfect, it's going to get a spot on the workbench. I'm definitely looking forward to having this 2000 watt load and being able to use it for testing. So as always, if something happens during that testing, I'll definitely revisit it in a future video, but at this point, not seeing any problems with it. I'm very happy how it turned out, and it looks like it's in fantastic condition now. Very pleased with it. So as always, thank you for taking time to watch, and until next time, take care. Goodbye for now.